Did anybody's classes get canceled yesterday or today?
Yeah.
Yeah. Oh, that's it's so hard to catch up after that. Well, hope it goes well for y'all if you miss class. Homework questions? Do you have them? Okay. You can email me if you have homework questions too. If you don't want to ask in class, that's fine as well. Okay. So where we left off in 6.7, we were talking about, or coming up with a formula for the work to lift, something out of a container, basically. And so this is where we ended up with. We ended up with the work is the density times the area times thickness times gravity times the distance of lift. So that's pretty much our formula, because we're going to work with this three-dimensional case, but we're going to translate it back to the 2D. So I guess that's one of the benefits of looking at integration is what we've primarily utilized it for outside of just like a math thing, like finding area and stuff, is when we're finding volumes of something in 3 dimensions, we can translate that into a 2-dimensional case and work with the 2-dimensional case to tell us something about 3 dimensions, which is kind of cool. But our work formula involving an integral will be density and mass are constants, so we'll take those out. Sorry, density and gravity, rather. And then the whole idea is that we have this formula, we slice through the container and sum all of that stuff up. So we have density times gravity times the integral from A to B. Area, we'll call capital A. That's going to vary. Thickness is going to give us our dy, the thickness of each one of those rectangles. And then the distance of lift. What would looking at the figure provided, what would the distance of lift be if we're pumping all of this water out of the outflow here? What would that distance be?
Y minus H minus X. Or Y equals H minus X. Or not X. H minus Y. Y.
Yeah, so all of our rectangles are filling up this region here. And they're coming out this way. So the rectangles stop here because that's our container we're pumping it out of. This is just like the pump, right? So all of these, the heights of the rectangles, they all vary. But that distance to whatever, it's top minus bottom. So H minus some Y value is the distance of lift. That's the formula we're going to use for work. Let's identify these things. That's the density. Rho is the density. So this is the density of the substance in the tank, gas, whatever it is. Usually we're dealing with water. The density of water is 1,000 kilograms per meter cubed. And of course gravity, 9.8 meters per second squared. A of Y are the areas of the cross sections. And the area of the cross sections vary it depends on the shape of the tank or the vessel or the container, whatever that happens to be. H is the top of the outflow. Usually it's the top of the tank, but not always. It just varies from problem to problem. So usually top of the tank, but not always. So the h minus y, as we said, was the distance of lift. Our bounds, A, typically the bottom of the tank, or container or vessel. And B, not necessarily B is the top of the outflow, because sometimes we might have a tank with an outflow pipe coming out of it, but B is always the top of the tank, wherever we stop with our cross sections. Whatever that liquid we're pumping out is the top of the vessel we're stopping, so it's top of the tank.
Top of the water level.
Yeah, you can think of it at top of the water level, yeah. Top of the tank, and the bottom of the tank is self-explanatory. But yeah, I guess we should be a little bit more careful on what we say the top of the tank. Maybe we should say, because I guess generally the tank doesn't have to be completely full of water, so we can just say the top of the liquid level. Yeah, sounds good. Yeah, that makes more sense. Well, you'll notice in that formula for the work that is done, there's only two things we need to find. Only two things vary. The h minus y portion, and again, that's just strictly determined by the height of the tank or the outflow. The tricky portion in a lot of instances is finding the area of the cross sections, just like at the beginning of 6.3, where we had to find the area of the cross sections that gave us that volume. So that's usually the trickiest part. Everything else is usually very straightforward. All right, do y'all have any questions on that? So our first example is we've got a cylindrical water tank. There's a height of 8, radius of 2. If the tank is full of water, how much work is required to pump the water to the top of the tank and out of the tank? And then will it take more or less for the same work to pump out water if the tank was only half full? So we're going to use that formula. I guess it's probably easier to find h minus y first. So here, h minus y is what?
8 meters.
Yeah, so remember the water level's here and we're pumping it out. It's totally full. But so then all of our rectangles are going to range from here to here.
So B is also 8 meters?
Yeah. But h minus y would be what in this case? So like, what's the location of this particular rectangle? If this is h minus whatever that y value is, right? This is, sorry, 8 minus 0, right? So that the height of the tank is 8. So that's just 8 minus y. That's just 8 minus y. And we'll find the area function. So our cross sections are what? They're all circles. The area of each circle is pi r squared. I guess most of the time we've been dealing with situations where the radius would change based on the function from like 6.3, 6.4. The radius here doesn't change, it's always 2. This one's not too involved. The area of all cross sections is 4 pi.
Oh, so that's our A of y?
That's your A of y. That's our area function in terms of y. It's just a constant. So that's really all you need in that formula. We're dealing with water, so we know that the density is 1,000 kilograms per cubic meter. We know gravity, 9.8. What's A, the lower bound of integration?
0.
0, if we put this thing on the origin, A is 0. And B is 8. All right. So, maybe we have kind of situated like that. So the work is integral from 0 to 8. Area times height. Mass times density, sorry. And so that's it. That's the formula that calculates work in that situation. So I don't know what that is. 4 pi times 9,800. It's a pretty straightforward function to integrate.
So you can bring 4 pi out?
Yeah, 4 pi constant. We'll just integrate the 8 and the negative y. I'm not sure if whatever that is. I didn't actually multiply this out, so I'm not quite sure what it is. So we end up with that, which gives us, should get quite a large number, 3940,813.825. The work we've done here, what are the units?
Joules.
Yeah, they're measured in joules because we've got kilograms, meters cubed, over meters cubed. Here's meters per second squared. So we're dealing with kilograms and meters. Maybe we can write these out when we set this up. So our units here with the density times the gravity, we had kilograms per cubic meter times meters per second squared. What's the units for the 4 pi? Is what?
Square meters?
Yeah, square meters, because 4 pi was an area. What are the units for the 8 minus y?
Meters.
Also meters?
Also meters. And the units for dy,
Also meters.
also meters. So we have, these cancel, meter squared cancel here. We have kilograms per second squared times meter squared, which is a joule. So make sure, if you can remember, it's sort of important, but I was always terrible with remembering my units, so I won't penalize you for getting units, but a lot of you are in physics, so you're probably already familiar with units and not leaving them out. So, do y'all have any questions on that setup? Does that make sense?
For work, are we always going to integrate in respect to y?
Not always. We're just thinking about usually tanks or whatever. They're situated like this, and so when we slice through them, those rectangles have a thickness in this direction. Yeah. I mean, I suppose we could tip the tank to the left and think about it going that way too. So you could do with respect to x. And in fact, if this were 8 minus x dx, this was from 0 to 8, x equals 0, x equals to 8. Doesn't change anything. It's still the same answer, right? Yeah, so I mean, for all intents and purposes, that's just a dummy variable. That could be t, dt, 0 to 8 in terms of t.
And then,
Yeah.
and then we gotta do it from 0 to 4, right? And see if it's the lesser or more equals to.
Oh, yeah, for the second part?
Yeah.
Yeah, so to pump water out of the tank, if the tank is only half full, right? So if the tank is half full, then this is the water we're pumping out. So the only thing that changes in that formula, the tank is still the same. The only thing that changes are the bounds, right? Because we're only lifting this out from here, all of these rectangles to here. So that's the only thing that changes. Oh, I forgot my 4 pi. So it's half full. So then we can just compute that, look at what is the difference, which one requires more work. Maybe we'll call that part B. I know it didn't ask, but how about if the tank is full? But we only want to pump out half of the water. What would the work for that look like?
Do the same thing with integral from 4 to 8.
Integral from 4 to 8. So the tank is full, but we only want to pump out this half. Right? So from 4 to 8, pumping this half out. there, don't remember. I don't think there is. Let me think about that. Do y'all have any questions on that? All right. So we have a cattle trough, height 1, horizontal sides of 1/2, and 1 meter, 1/2 and 1. Assume the length of the trough is 10 meters. How much work is required to pump the water out of the trough to the level of the top of the trough when it is full? We'll remind ourselves again of the formula. So remember, A of Y is the area of the cross sections. So our cross sections are what?
Rectangles?
Yeah, our cross sections, when we cut through here, our cross sections are rectangles. I don't know, maybe we just start off by saying it's length times width. Which one varies, which one doesn't? Yeah, so we have one dimension that doesn't vary. Length or width, however you want to label L or W, W or L. Because we know the trough is 10 meters long. Okay, before we continue here, what would our H minus Y be? If the trough is full and we're pumping the water out. 1 minus Y. Yeah, 1 minus Y. So now, what do we need in this area function? What do we need to happen?
In terms of what?
Yeah, we need the width of the cross section to be in terms of y. So we need w as a function of y. So we're just trying to measure that linear dimension. Okay, so there's the face of our trough right here. We know these bounds here are going to be on y from 0 to 1, right? So we're really not concerned with the horizontal aspect of that. What we're concerned with is the equation of this line right here. Because the width that we're measuring is that width. We see, depending on where we're at in the vessel, the width does vary. It varies all the way from 1/2. So here it's 1/2, and then up at the very top it's 1, but it varies in between. So we can think about the length of that, or the width rather, as the right minus the left, or it's 2 times this length. So we'll just take that and double it because that's twice the right minus 0. Y'all agree? That way we'll just find one equation of this line instead of finding the equation of both of these lines. And again, that was set up. We centered the trough at the origin so we could use symmetry. If you put this thing over here like this, you put that over there, then you would have to find the equation of both of these lines. So that's well, we know that the original base is half a meter long, but we're cutting that in half too. So this goes from 0 to a fourth, right? So this point here, 1/4, comma 0. What do we know about this point? Yeah. So again, the length of this top that's 1, but we've cut it in half, so that's a half. And the height of that tank is 1. So that height is 1. So whatever you do, however you deal with lines, the point slope formula, or if you use y equals mx plus b, solve for b, whatever you do, doesn't matter. We just need the equation of that line. Okay. So we'll put the equation of our line here. The equation of our line. Let's do y minus y1 equals to the slope times x minus x1. So now we got to find the slope. What's the slope of the line? It's 4. Yeah. So we have the change in y from 0 to 1. Over the change in x, we go from 1/4 to 1/2. That's a change of a fourth. So the slope is 1 over 1/4, which is 4. Oops. So we've got the equation of the line, y equals to 4x minus 1. Remember, we want that's the width here, we need to double that, but we also want this in terms of y. We want the area function in terms of y, not x. So we solve for x. So that's the equation of that line. And we said the width was twice the distance from that line to 0. So we have twice the right minus the left. or twice right minus 0, which is twice this thing here. Is that okay? Do you have any questions?
Sorry, we did a 2.
No, it was this 2 right here.
No, yeah, I know. But like,
Oh, because we're just going to calculate that one and double it to get the width, the actual width. You could find the equation of this line if you wanted, and then just subtract that minus that. I don't know. Think of the width here as 2x. Yeah, so we have to multiply that by 2. And that does give us so now we have the width of the trough as it varies in terms of y. We have h minus y. So that's pretty much all we need now to put into the work formula. Our work is gravity times density, integral from, what are the bounds?
0 to 1.
0 to 1 because we're pumping all of this water out from a y value of 0 to a y value of 1. Okay. 0 to 1. The area function. Remember, area was 10 times the width. Let's go ahead and finish this out. 10 times the width, which we found was y plus 1 over 2. So at 5 times y plus 1. Okay. And then what was it? Oh, 1 minus y. It was 1 minus y. Yeah, we take the 5 out, it's a constant. I don't know what that is. I'm going to do that right now. And then this is the integral from 0 to 1. Yeah, difference of squares, 1 minus y, 1 plus y. Honestly, none of these in this section that I've seen turn out to be difficult antiderivatives. The difficult part is just setting it up. So we should come out with the work to be $32,666.67 joules. So, are there any questions on the setup here? So a slightly different work problem. We're still calculating work, but we're not quite given what we've been given with these last two. So 30-meter long chain hangs vertically from a cylinder attached to a winch. Assume there is no friction and the chain has a density of 5 kilograms per meter. How much work is required to wind the entire chain onto the cylinder using the winch? So we'll set this up. Set up only. I don't know, maybe you have this kind of situation here. Chain. What is it, 30 meters? And we're given the density of the chain, but notice the density isn't like a mass per volume. What we're given here is a linear. So we've got a linear density, not like a area or a volume. So it's slightly different than the last two examples because the last two examples where we're thinking again of a volume and translating that into this one-dimensional or this two-dimensional space, talking about the area. But here it's not that's not the case. You don't have a volume we're trying to think about the area of. So it really is just like this very straightforward linear type of thing. So how would we go about finding the work?
Use the same formula. Density, gravity, center of gravity, rho beta B, A of y times h1 dy.
Okay, I suppose we could attempt, but what's the area of our cross sections? What if I did, my cross section looks like that? What type of cross section is generated when you slice through a line? So we're not really able to find an area function because we don't have an area per se in the regular sense of an area function. But what else do we know about work? Work is force times distance, yeah. What do we know about force?
Mass times gravity.
Yeah, it's mass times gravity. Is that going to help us?
Yes.
We're-
Because we know what the mass of the thing is.
Yeah, so the mass is what?
150 kilograms.
So how do you get that?
If the density is 5 kilograms per meter and you've got 30 meters, multiply those together.
Okay. So do we know, what did we talk about last time with mass and density and all of that stuff? What do we know? Is what?
Density or the mass times volume. Density times volume.
Density times volume, right. Mass is density times volume, but we don't have a volume, do we?
Well, the volume is.
Yeah, we have a length. So remember we said density, depending on the situation, it's mass times volume, mass times area, mass times length. So that's how we're going to utilize the information that's given to us. Density times length. I don't know if my rows are okay or not. Okay. And so I guess when we look at it as density times length times gravity times distance, one of the distance is going to be 30. The length, in the sense, we wouldn't want that to be 30 as well. So I guess there is room for confusion when we look at it this way. I don't know which one it makes sense, but the length or this distance, one of them has to be this dy right here. So we'll go from where to where. We can really set this up however we want. But we haven't put a coordinate system to this yet.
0 to 30.
Yeah, why not 0 to 30? So we'll go from 0 to 30. And what do we have in here? dy. It's one of those linear measurements. Really, we just have density times length times gravity, right? So we're given density, we're given length, we're given gravity. 30 density. So what should go there? Just the 30 or something else? Yeah, good. Because all of those have some height wide. That height that each rectangle is at is varying in that chain, right? So this distance from here to here is 30 minus y. Same with the distance from here to here. there's our, I guess if you want to think about it, length, density, gravity, thickness, or distance. Do you have any questions on that? So there's our setup. We'll actually need to compute this because Part B builds on what we've done here. So Part B asks how much work is required. We've got the work here, haven't calculated it, but how much work is required to wind the chain onto the cylinder if a 50 kilogram block is attached to the end of the chain. From here we just calculated the work to wind the chain. Here we want to know what's the work required to do something additional. So what would we do here? Any ideas?
Break the weight down the block into density and gravity.
Right, density, gravity, and mass would give us the work, wouldn't it? Yeah. So I guess there's a couple of ways to think about it. The total work is equal to the work of the chain plus the work done by the block, I guess. And the work of the chain was computed or set up to compute in Part A. So suppose we could look at this in a couple of ways if we needed to. The work of the block, mass. What did you say? Mass times gravity. No, and then you broke down mass, right?
Right.
So density times length. Is that what you said? So how exactly would that look? I mean, or would we need that?
I just like, okay, we find density because we have its weight and we know what gravity is.
Yeah, we know it's mass.
That's mass, that's right, we already know.
So maybe we'll come back to this. I mean, nothing really varies here. If I've got a block attached to the chain, that block is like this point on the chain that's just being raised up, right? So really, there's no need to involve an integral with this because it's just like this point weight plane, or point in the plane that we're raising up with the chain. So should we continue this? Does anybody have any further suggestions on how exactly that would look? Or should we try to build it into an integral? So we could take its mass times the distance of lift, which is 30, right? That point would go from 0 to 30, times gravity. Mass times gravity times distance. Does that give work?
Yes.
Yeah.
That makes mass and gravity is more.
Yeah, exactly. Yeah. Mass times gravity is a force, times distance is work. So mass times gravity times distance. Again, just imagine a point on the end of the chain. It travels from 0 to 30. It's the fixed distance it travels. So whatever that comes out to be in joules, we would just add to Part A, and then we have the total work of the system. Since since we need this, let's go ahead and compute this. Anybody compute that yet?
220,500.
Say that again?
220,500.
225. Like that?
Yes.
Did anybody get something different?
I got the 5 and the 10s place.
Yeah, I got 22,000.
Yeah.
I got 22,000.
Uh-oh.
20,050.
Oops. So we're basically saying we're off by a magnitude of 10.
What did I do?
Well, let's see.
It is 20,050.
Yeah. So you got, did you get, somebody else got it? I got 3 people getting that. 4, 5, 6, 7. I think that's enough. Let's see. We'll go with that. So that's the work of the chain. Plus the work of the block, whatever that is,
14,700.
14,700.
That one I got.
You're on.
Dude, get you figured out. 14,700. So that's the work of the block. So this is our total work. What is that? 0.5. 0.5.
36,700 times 0.
So total work. The same idea is applied if we want to use an integral. So work, the total amount of work is the integral from 0 to 30. Our first, the work of the chain is that 5 times 30 minus y. Plus what? Well, let me do it this way. So gravity times all of this, and gravity times this. 50. So notice that would give us the same thing. Here, work of the chain. This is the work of the block. When we integrate this, 9.8 times 50 y, and then we evaluate that from 0 to 30, so that's just 30. So it's 9.8 times 50 y from 0 to 30, 9.8, 50 times 30, which is what we had here. So when you integrate this portion right here, plug in the bounds, you're going to get this portion right here. It's the same thing. I guess technically we didn't have to use an integral if we didn't want to. So problems on the exam from 6-7 will be these tank kind of problems, not like these. There might be one spring constant kind of problem as well, but the other ones will be related to pumping water out of a tank or pressure on the face of a tank. Do y'all have any questions on that example? So force and pressure we'll look at next. So we're just talking about the pressure on this face. We're not concerned with how much water is actually behind all of that. So we'll start with, we'll kind of break this down like we did with work. We'll start with force is mass times gravity. So keeping in mind, we're not looking at a volume anymore and then asking a question about, well, what's the area function? Here we're looking at an area, so what do you think we're going to ask about? Not a volume. So we had a volume and then we asked, what's the area of the cross sections, and we worked with that, right? Here we're looking at an area and our cross sections are going to be, yeah, lines. They're going to be a linear dimension. So we went from 3 dimensions, what's happening in 2 dimensions, work with that. Here it's analogous because it's where we have 2 dimensions, the area on the face, we're kind of bumping it down into 1 dimension, which is a linear. So that's kind of where how we're breaking this up into. So again, mass, density times volume. That's volume. We'll just say is area times thickness times gravity. And we don't stop there because we don't want to think about it in terms of the area. We want to think about it in terms of a linear dimension. So we're going to break area down once more. So we have density times, I guess we can say length times width times thickness times gravity. And maybe, I don't know, maybe it makes more sense to say length and height. I don't know. But we are focusing here on this tiny little strip. So once again, density, gravity, constants, thickness of each strip or line is dy. The height is just like very comparable or the same actually as the height in the previous models. We go from this y value to the top. So if this is, if this is h, well, they're actually calling it a, and then it's a minus y. just to keep the notation and formulas consistent, we'll just call that h minus y. And notice the length is the length of the line. So that will also vary depending on the tank. So that L is actually a varying function of y, L of y. Well, your textbook actually calls it W for width function. So I guess it's just a matter of convention. What do you want to consider that, a width or a length? Your textbook calls it a width, but it's the same idea. Here, I'll call this width times height for area, just so it's consistent with your textbook. So there's how we're going to measure force on a face like that. And I think when we see this formula and compare that to the work formula, it might give us it might make it easier for us when we're dealing with these problems to know what we actually need to find, because they're virtually the same thing. Work was density times gravity from A to B. This was A of y, h minus y dy. So the only difference is if we're talking about force, we're looking for the width function, right minus left. If we're talking about work, we're looking for an area function. It's really the only difference there. Yeah, so I guess the only thing we should point out here is W of y is the width function. So sometimes it's like it's like a dam where it's holding back water. Sometimes it's like a viewing window in a swimming pool or something like that, but that's what we're measuring with W, the width of the face. Which, of course, is the cross-section that we're cutting in. So, I mean, I think that's good because the formulas are so similar. But yeah, it can be detrimental, I guess, if you're not careful of which one you're using. So do y'all have any questions or comments or? No one's asked. No one's asked why gravity is negative. I'm surprised no one's asked that.
Why is gravity?
I didn't want you to ask it. I was just surprised you haven't. So yeah, I think the text, typically work is a positive quantity, right? Typically. Maybe the situation is we want to think about it as the work done against gravity. Because if we had like a negative work, we might say, well, that's negative pointing in the same direction as gravity. So is that work in the same direction as gravity, or is it in the opposite direction of gravity? So we want it to be positive. So we know it's positive and gravity's negative. We're working against gravity when the outcome's positive. I believe it's typically positive anyways, but there are instances where work would be negative. I'm not quite sure, but I think when the force, what am I trying to say?
Isn't it like work on a system versus system, like work done on a system versus system done on something else?
Right, work done by the system or work done on the system. So is the system internally working, or is there work external on the system? If there's work external to the system or on the system, then work is usually negative. If it's work within the system, it's positive. So yeah, gravity's positive, so the work comes out positive. So maybe we'll think about this, take a break, and then start looking at it. I will say that if you look at this and compare it to that trough example where we were calculating the work, you should find a lot of similarities with this example and that. In fact, this one is actually easier to determine the equation that'll give us the width function here. So let's just think about this one and talk about it once we get back from break. Do y'all have any questions before we go on break? Yeah.
So like, what if you calculate like a surface area, and then like the amount of weight being received, would that be pressure, or would that be?
Yeah, pressure is force times area. So you can calculate surface area and the pressure. Yeah. leave that running one day just to see what y'all are talking about.
Oh, God.
I'm just kidding. I respect privacy. So what's this gonna look like? Calculate the force on the face of the dam. And really, so you should just remember these two formulas and how to what goes where, because I'm not going to deviate from this on the exam. There's not any, in my opinion, there's not any curveballs on the exams.
So then would you just like find like the coordinates? You just kind of do like subtract, right?
Yeah. Right. Yeah. So here's how we want to set it up. Once again, keeping in mind that when we talk about the width, we're talking about the width of each cross section that takes to fill that up. So we could, in a situation like the last one, we could find both equations of the lines and then subtract right from left to determine the width. Or we could center this so that we could utilize symmetry. So we could center that and just do twice x, or twice the right minus 0. And it's even more convenient because one point is already at the origin. If you want to try to establish this cone somewhere else out in XY coordinate system and come up with that equation, you'll find that you get the same work. That'd be a good thing to practice. Not that you would have to, because with these types of things, you're totally free to orient it and set it up however you want. So yeah. Uh, 10 comma 30. What do y'all think? Is that 0.10 for its x value here? Half this, yeah. And then the height of it is 30. What's given to us is 30. Okay, so much easier to establish the equation of that line because it doesn't have the y-intercept. So what is the equation of that line? Yeah, y equals to 3x. Rise 30, run 10, slope is 3, y-intercept is 0. But again, dy, we want that as x equals 2. So that is y over 3 equals to x. All right, the bounds go from where to where? 0 to 30. The h minus y is what?
30 minus y.
Yeah, 30 minus y. And the width function is what? Okay, remember y over 3 was just this boundary.
Y over 3.
Yeah. So the width is twice this right here. Yeah, so it's twice y over 3. So let's take out our constants. We've got this over 3. times 2, integral from 0 to 30, y times 30, minus y times y. Do y'all have any questions on the setup? Huh? This one?
The 2 on the left.
Yeah, this 2/3 here.
Just distribute the y.
Yeah, and distributed the y. So that comes, should I get that to come out to be 29,400,000. What are the units for force? Newtons. Yeah, capital N newtons. Any questions?
So that's just that water column that's kind of over the greatest width of the base there, exerting pressure on the dam.
Right, yeah. So we're measuring just, if we could imagine that water is on this space right here, we're just measuring pressure on this space right here. I don't know if any of y'all had a chance to watch the pressure videos. The hydrostatic pressure doesn't depend on the volume of water that's behind it. It only depends on the width, how that varies, and the height of the dam itself. Which, I don't know, I found surprising when I first started.
The water could be halfway up and it doesn't matter.
Yeah. Well, if it were halfway up, you'd have less pressure because you'd only go from 0 to 10, or sorry, 0 to 15. So it would matter, the height of the water level, as well as the area of the face, basically.
But like the size of the reservoir behind it.
Right.
Yeah.
Exactly.
Just a millimeter of water.
Yeah, even if it's just like a tiny sliver of water behind it. It's crazy. I can't explain it very well. The videos I posted are there for that reason.
The pressure would just change if you were to remove the wall, how hard you would get hit by the
Yeah.
wall behind it.
Yeah, I guess
but
you
not
could-
the pressure on the wall.
Yeah, right.
Because this is force, which is measured in newtons, but can you also apply the pressure? I know pressure is like usually measured in PSI.
Mhm.
So
Yeah.
are they related? Is it like force and pressure, or is there some different?
Well, I don't know as far as terms of PSI dealing with pressure. I guess that's just one particular way to measure it.
I don't know if we have like have a conversion from newtons to whatever. I don't know what the standard is. The SI is on the pressure.
Oh yeah, I'm not sure on that either. In one of the other pressure videos, they were saying, if I don't know, some football player, I forget his name, was wearing a stiletto heel, would you rather have him step on your foot, or would you rather have an elephant step on your foot? And it was the argument was you'd rather have an elephant step on your foot because it's distributed over a greater surface area than a 300-pound human being with a tiny little heel going into your foot. It's a small surface area. That's a lot of pressure in just one spot versus in that spot.
Plus he's probably gonna fall.
So,
Yeah, that one probably.
all right. So a couple of these are in your homework. So let's look at. They're very similar, but let's get a sense of what's happening here. So you have a diving pool 4 meters deep full of water. Has a viewing window on one of its vertical walls. Set up an integral needed to find the force on a square window that's 0.5 meter by 0.5 meter square. with the lower edge of the window on the bottom of the pool. Viewing window.
There'd be a viewing area lower than the bottom of the pool, right?
That was 0.5.
What?
There's a viewing area that's lower, like the floor that's lower than the bottom of the pool. If you're looking through a window that's 2.5 feet tall.
Yeah. Well, 4
Doesn't
meters.
make more sense to put it in the corner.
4
rather than the
meters.
center of the wall like that.
At the bottom of the pool, though.
Uh-huh. Yeah, so it's just a square window at the bottom. How are you thinking it's down here?
Like somebody's outside the pool looking into the pool, or what?
Yeah, I guess. I don't know.
Think about like aquarium, like there.
Viewing window on one of its vertical walls, the lower edge on the bottom. Okay, so yeah, something like that. I mean, I guess you could put the viewing window in the center, but it does say it's on one of the vertical walls, so honestly, if you put it in the center, it doesn't change anything. So we've got, this is 4 meters deep. And the window, 1/2 meter by 1/2 meter. Okay. And keep in mind, what we're measuring is the pressure on the viewing window, not the pressure on the entire structure. So our cross sections are just going from here to here. What would anyone want to take a shot at what the force function would look like? What would the bounds be?
0 to 1/2.
0 to 1/2, right? Do y'all agree?
Yeah.
Because that's the bottom of the viewing window, the top of the viewing window is 1/2. Okay. What's the width function is always 1/4, so that doesn't change. Or sorry, 1/2 instead of 1/4. So the width function is constant. Well, or is there? So this is W sub y. Then what do we have to multiply that by? Huh? Yeah, h minus y. What's h here? Is what I heard it. It's 4. Yeah. Because we've got the water is all of this. Remember, the h is the top of the tank that contains the liquid. So we do have to multiply this by 4 minus y. Yeah. Okay. You all satisfied with that? All right. Are there any questions? So, with that in mind, what's going to change here with the with number 9? The window is same window, but it's 1 meter from the bottom of the pool. Right. Good. Yeah. So the bounds are the only thing changing because the pool is still 4 meters tall. Yeah. No.
1 to 1.5.
1 to 1.5, right. So here's the viewing window now. Length 1/2, height 1/2. Cross section, still the same. Cross sectional width, still the same. But this time, those y values range from here to here. We're actually, the y's are starting here at 1/2 and going up another 1/2. what changes there.
Oh, so say contact distance.
No, because it said it would come to the bottom, so it's.
Oh, well, yeah, 1 meter from the bottom, yeah. So where should we start? Yeah, this starts at 1, and then we go up another half unit. So 1.5, yeah. And you said that, I just totally, I just ignored you and did the wrong thing. To 1.5. All right, thank you. Let me write down the answers if you're going to compute these. So, or rather, number 8. Number 8. This force is 9,187.5. $9,187.5 for 8, and for 9, 6,737.5. And then the last page is just a summary. The formulas are not provided for density, or sorry, for mass, for work, and for force, so you have to know those. Also, the spring constants, you should know the force is kx. Okay. Are there any questions before we move on? So 7.3, the last section in our first unit, deals with the hyperbolic trig functions. We're not going to do a lot with these. If you're interested, the exercises in the back can sort of explain some of the applications. But you've seen like telephone wires hanging from pole to pole. Like those things are modeled by hyperbolic trig functions. Primarily, we're going to focus on, and we'll see that there's a analogy to the circular trig functions here. Before we actually look at that, though, this is how we define the hyperbolic trig functions. Just like the circular trig functions, all of the other ones are defined in terms of sine and cosine, right? Their reciprocals or their quotients of sine and cosine. The same thing is applied to the hyperbolic trig functions. Hyperbolic sine and hyperbolic cosine are the main ones. Everything else is built off of them. So this is the function's name, SINH, and then there's our input. So that's like, just the name of the function. And this is pronounced sinch. And this is pronounced kosh. I don't know how to spell that. Kosh. Rhymes with gosh. So notice they're actually defined as their exponential functions. Defined in terms of exponential functions, anyways. So you should know these two. You should know their definitions. That's how we define hyperbolic sine and hyperbolic cosine. So I'll put a red star on things, or a red box around things you should know for the exam. Yeah, we're not gonna do a whole lot with this stuff. I think there's like, 10 or more questions maybe. But we do need to at least introduce.
How long is the test? How long is the test, roughly?
2 hours and 15 minutes.
Like questions?
Oh. I don't know. 10, 15 maybe? Something like that, yeah. Okay, so when we're asked to find the derivative of sinh, I guess there's two ways. We could use the definition of the derivative, or we could just say, well, that's tedious. I don't want to compute a limit. I can just take the derivative of its definition, e to the x minus e to the negative x over 2. So let's see what we get. We take the derivative of sinh. That's equal to the derivative e to the x minus e to the negative x over 2. So what is the derivative of all of that? Yeah, the derivative of e to the x, derivative of e to the negative x, and then our constant 1/2 stayed out. Is what?
Sine, cosine, what's the
Yeah. So we see e to the x plus e to the negative x over 2 is cosh. So the derivative of sinh is cosh x. So yet another similarity. How about the derivative of cosh? Maybe. Let's see.
I have a feeling.
Oh, I don't know. Whatever. E to the x plus e to the negative x over 2. So that's the derivative of cosh, which equals e to the x minus e to the negative x all over 2. What's that? Yeah, sinh. Huh?
Is that a question on the test?
Yeah. Maybe, I don't know. Could be.
Should be.
Could be. Okay, so let's, well, I don't know. If you're very intrigued by this, you can find other supplements online, some good animations and stuff. There's a lot of videos that aren't good, but there are some that are good. It's hard to pick sometimes. But our unit circle, the analogy of the circular trig functions come from the unit hyperbola. So just like on the unit circle, when we said let's measure this angle here. I don't know, we call it theta or t or something, whatever. We said any point on the unit circle xy, call it xy, can be found in terms of sine and cosine, right? So cosine of theta would give us what? X, or x over the radius. Radius here is 1. And the sine of theta is equal to y. So then the Pythagorean identity, sine squared plus cosine squared on the unit circle makes total sense, because cosine is x, sine is y. Cosine squared plus sine squared is equal to 1. Right? That's where that comes from. unit hyperbola, how do you think you define the unit hyperbola? All right.
X squared minus y squared.
You're right. Or x squared minus y squared equals to 1. Remember the hyperbola as a conic section. Remember the more generic formula? Is this. Right. So unit hyperbola, center 0, 0, radius 1. Or, not radius, but equal to 1. Just kidding. So the idea is, remember these things have, the hyperbola actually has an asymptotes that are built in. I'll do my best. Anybody remember the asymptote, the equation for the asymptotes? Yeah, x equals y, y equals x. So that tells us, in terms of this angle here, if we look at it comparable to the unit circle, I would say, okay, here's a point x, y. And I look at that here. That's the analogy on the unit hyperbola that we had with the unit circle. There's a relationship between the area of this piece and the area of the circle. Again, if you're interested, you can, seek further supplements. It's not really, I don't think it's that important for the little amount of work we do with these things to know that. But there's the analogy at its most basic level anyways. What do you think they call it the fundamental identity. What do you think the fundamental identity here is? So let's write this out again. We'll call this, I guess we could call this theta, not to be confused with the other theta. So maybe we should call it t. I don't know. This is t. Cosh of t is x, and the sinh of t is y. So the fundamental identity that relates these two, again, is based off of the equation for the unit hyperbola. Cosh is x, sinh is y. So our identity, we wouldn't call it Pythagorean, I don't think, but cosh squared minus sinh squared is equal to 1. They call it fundamental because it's directly built into the constraints.
You're using t because there's not really an angle or something.
Yeah, I mean,
Using the distance from the origin of the axis to the, I guess, the apex. Well, not the apex, but like from the origin to the point of one of the
yeah. So what happens if we did consider this an angle like we did on the unit circle? Well, we can go up to a certain extent, right? But as that angle approaches 45 degrees, the area underneath or bound by this keeps getting larger and larger and larger. So it's not, it's related, but it's not clearly two different scenarios, unit hyperbola, unit circle. You've got some different constraints. Okay, so that's based off of that. And again, we've already seen the definition for, if I wanted to find this point x, then I know what hyperbolic cosh of t is, e to the x, etc., right? So we know how to define these two things in terms of exponential functions. And so like working with things like number 3, find what sinh plus cosh is. We think about it in terms of, well, sinh is e to the x minus e to the negative x over 2 plus cosh, which is e to the x plus e to the negative x over 2. So the e to the negative x's cancel each other out. We've got 2 e to the x over 2, which is just e to the x. Okay, so we can work with those things via their definition. Nothing like terribly shocking there. The hyperbolic tangent is defined as sinh over cosh, just like the unit or the circular trig function sine over cosine. I can't write out phonetically what that sounds like. Tangent. That's what it is, tangent. Or you could just say hyperbolic tangent. I think it sounds cooler. Okay. You should. So definitely know sinh, cosh, and tang. You should know these three.
How do you pronounce the other three?
If I remember. Cotang, yeah. That's sech. That's cosech. All right. The identities, definitely the fundamental identity here. The other two are the other. Yeah. You should. I mean, I'm not going to test over all of it, but I can't tell you specifically. I don't want to limit you. I don't want to just say, hey, just know hyperbolic sine, and you forget everything else. That's not doing you any favors. So those things, all the other stuff we won't really deal with. We won't need the other identities nor deal with the cofunctions. So we already saw the derivative of sinh was cosh, derivative of cosh was sinh. So we need to know those two formulas, derivative formulas, and the derivative of tang is sech squared. Should know those. As far as the integrals go, the first three integrals as well. I'm gonna make it. I'm right there with you. All right. So yeah, well, the stuff we're doing in this is about the level of content that will be over the hyperbolic trig functions on the exam. So prove that the derivative of hyperbolic tangent is hyperbolic secant squared. What would the easiest thing to do here be? Yeah. So here's a couple of things we have. We have options. Here's one option was to take the derivative of two things we already know. Remember, tang is sinh over cosh. So we can take the derivative of that quotient. What else can we do?
Or wait, no, so we're
Yeah, we're prove this equals this.
With the quotient rule, it should work out.
Yeah, so the quotient rule here totally works out. Or, it's a derivative, so just we could use this. Limit as h goes to 0 on the difference quotient. Is That is the actual definition of the derivative. Not very easy, because we don't know, we're not familiar with identities for that. We also had it might not be as helpful, but we also had the exponential definition. I mean, we could take the derivative of this, but we'll end up with stuff in terms of e to the x, and we don't know the definition of hyperbolic secant squared in terms of e to the x. But if we did, that's another option. Oops. Definitely the first thing we mentioned was the easiest. So derivative of the quotient rule says we take what?
Loading high, high, low.
Okay, yeah, so let's do it that way then. So bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared.
Can't you just plug in like EDX for sine and cosine or whatever?
Yeah, you could use their exponential definitions too. Is that what you did?
Yeah.
Did you get it to come out? Okay. Again, the problem with that is we don't know, once we end up with the derivative of all of that exponential, it's going to be another exponential, but how do we know that exponential we end up with is actually set squared? Because we don't know the exponential definition of that. So we'll have to stick with this, see how this goes. So the derivative of hyperbolic sine was what? Yeah.
Cos squared minus sine, or cos squared x minus sin squared x over.
Oops, that's just x. Where's what's in? Yeah. And then we have cosh squared minus, this is sinh squared, all over cosh squared. Then what? Yeah, what is cosh squared minus sinh? It's 1. So this is 1 over cosh. So just like you did in Calc 1 where you said, oh, here's the derivative of sine and cosine via the definition, well, all other trig functions are in terms of sine and cosine. So then you can just apply quotient rules or power rules to find the derivative of the other trig functions. Same idea with this one.
Just give a look for a moment.
Sure, yeah, sorry. Is that all right?
Yeah.
Or negative sine? Derivative of cosine, cosh.
No, it's not like that. The same. They're not identical to the circular trig functions. Derivative of sine is cosine. Derivative of cosine is negative sine. Not the case with hyperbolic. The correct page. I mean, even if you look at the derivative of the cofunctions here, they're not quite the same because they don't come from the same figure. So, like the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. I mean that's comparable to our circular trig functions. What was the derivative of the secant function? Secant. Secant tangent, but the derivative of sec is negative sec tang. So there are differences because they're different, but it's an analogy.
Are these identities on the next as well?
Yeah, if you just want to print this page of the notes, you can get them.
It's in the slides.
I got rid of the slides because I didn't think they were everything relevant. I've already put in our notes. So
With inverse hyperbolic trig functions.
no, we won't deal with inverse hyperbolic trig functions. All right. All right. So y'all try that derivative of number 5. Anyone want to share what they got as the derivative?
I don't know, Brad, but I got x over cosh root x squared. Get out. That's what it is.
Somebody get something different?
So uncomplicated.
Here, I got x cosh root x squared plus 1 over root x squared plus 1. That's what you got. The applause meter.
Yeah. that right? Okay, let's see. So the derivative of sinh. So chain rule dictates that we leave the inner function alone. So we leave the inner function alone when we take the derivative of the outer, which is here. Then we multiply by the derivative of the inner. So that's another chain rule. The derivative of this right here is 1/2 times x squared plus 1 to the negative 1/2 times the derivative of what's inside. So don't forget that the second chain rule. So now we've got a 2 divided by 2. We've got an x up top with the cosh, and then the root of this thing is now on the bottom because of the negative exponent. What's this? Is this one?
So aside from what cosh represents, taking the derivative of all these is exactly the same. Just adding an h.
Yeah, with the ones we're looking at, sinh, cosh, tanh, yeah,
Okay.
that's it. And the h is to indicate that it is a different function too. Yeah, so. But yeah, pretty much. What's the antiderivative of cosec squared? Negative. Yeah. That was just formula. That's it.
That'd be a valid test question.
A what?
Valid test question.
This one?
Yeah.
No. This one would be. So how do we find the antiderivative of x sinh x squared plus 4? Yeah, u substitution. We recognize u substitution because we've got the product of two functions of x, one of whose derivatives or constant multiple of a derivative is sitting right here. So that's our candidate for u substitution then is x squared plus 4 du is 2x dx. Don't forget your differentials, dx, du. Those things do matter. Don't try to be neat. Don't just drop those differentials. It'll matter a lot too when we start looking at chapter 8, especially with integration by parts. It does matter. What?
Yeah, 1/2 du dx dx.
Yeah, if you want. Okay. So then the original integral turns into what?
1/2 sinh u.
Yeah? Y'all agree? Okay. What is the antiderivative of sinh? Yeah, cosinh. So we've got 1/2 cosh of u plus c. And then resubstitute. We're done. So none of those are terribly involved, I think. But again, that's more of a preview of what we could consider consider on the exam as far as exam questions. Does anyone have any questions? I do want to refer you to the textbook in the applications of hyperbolic trig functions. This is catenary or catenary, it just depends on who you ask. So that's kind of when you have the power lines hanging like that, or some suspension bridges have those cables hanging. So if you're interested, you can look at what is the difference between a catenary and a parabola. Because when we look at the hyperbolic cosine, I mean, it looks like a parabola, doesn't it? So there is a distinction between catenaries and parabolas, but it's very subtle. You know, like the Golden Gate Bridge, are those parabolas or are they catenaries? And so we can measure, then we can go and get into measuring the length of a catenary, where we'd use arc length with this function here. And we know how to integrate these. So then we can start looking at arc length, surface area, all of that stuff. Here's the velocity of an ocean wave problem. And then there's more in the exercises, probably under explorations and challenges, things like that. A falling body modeled here. Here, terminal velocity modeled here. So if you don't have to do these, it's just I suggest that you do look through these just to see what can I actually do with these types of things that we are studying. And some of them, these are more mathy things down here, but there are like a handful of actual applications where you can utilize these things. So just keep that in mind. I don't know that a lot of people refer to the textbook, but it is there. Okay, any questions?
I like it.
No homework questions? No questions on 6-7? Feel okay? So when we come back Tuesday, I'll have notes on the exam, tell you what the content is, and then we can look at review questions or homework questions, or what have you. I don't have a packet of review. The closest thing I have is additional exercises on D2L. That's as close as I get. And also I'm going to tell you kind of what's on the exam so you know what to focus on. So I feel like, I don't know, I hope that's sufficient. All right, well, I guess we can cut out early. See ya. Have a good weekend.